Welcome students to this course on Bayesian Inference. Our purpose here is to go through the Bayesian methodology and we'll see that how it differs from the Fisherian ideas. You might have aware of that particular topic, because usually people who follow the Bayesian, the Fisherian technique, they adopt the ideas of keeping the parameter of interest to be fixed and the likelihood or the data-based likelihood to be random. But here we will do that in a different way. Following the ideas of Reverend Thomas Bayes, what we will do here is that we first of all consider theta to be random, unlike the Fisherian ideas, and we will consider the data to be fixed. So the Bayesian people honor the likelihood and they try to draw inference on the parameter of interest by keeping theta to be, by keeping the data to be fixed, all right? So throughout the discussion, we will first of all develop the ideas vis-a-vis the Fisherian ideas, and then we'll go for some examples that will motivate why you are going to use this Bayesian technique, and subsequently we go for the consideration of prior for distribution of the parameter of interest theta, and then we go for posterior analysis. So this is what we overall what we want to do here throughout our discussion. Let us give the name of the topic of our discussion as Bayesian inference. Come on. The Bayesian inference, we will discuss some methods and computing. So initially, let's try to differentiate what is Bayesian inference and what is Fisherian inference. You see, the Fisherian approach, what we call the classical approach or frequentist approach, sometimes I will say classical approach, sometimes I may mention that it is a frequentist approach. But anyways, the classical approach treats the parameter of interest theta to be fixed and draws repeated samples from using that fixed theta value, okay? And in the Bayesian approach, theta is regarded as the realized value of a random variable, script theta, which has some distribution or prior distribution with the PDF or density function being f theta. Let's look at the comparison of these two techniques. In the classical technique, it stands that the parameter is fixed and data being random. So if we have different sets of data, because data is random, then you have different inference because the parameter remains fixed but the data varies. On the contrary, if you look at the Bayesian approach, where data is kept to be fixed in the operational sense, but the parameter varies, it has some uncertainty, so it's a random. But in both cases, the interest is to draw inference on the parameter theta. On top of that, in the Bayesian inference, we honor the likelihood. Once the data are available, throughout our experiment, throughout our inference procedure, we keep the data to be fixed based on the same likelihood. And that we do not in the case of classical technique. And also, we talk about the distribution of theta, which is our prior belief on the behavior of theta, that usually it is not taken in the case of classical technique, where theta is assumed to be completely fixed. As earlier I mentioned that in Fisherian technique or Fisherian ideas, the samples are random, so inference will vary. Inference on theta will vary from sample to sample. So if samples of the same size are drawn repeatedly from a population specified by the parameter theta, a confidence interval for theta is calculated, then the interpretation in the Fisherian ideas is that in 95% out of 100 cases, 100 such sets of samples, in just 95 cases, you can see that the parameter theta is contained in the corresponding interval. Must note that in that case, the interval varies over sample to sample. But on the contrary, if you look at the Bayesian confidence interval, what we call the credible interval, the credibility concept comes because of the variation in the prior. What strong prior you take, it depends on that, how credible it is. Okay? So when you consider the credible interval for theta, then it makes sense that you give the probability statement of that random parameter theta. So probability theta that lies in the corresponding credible interval is 95%. Given the data, so as I said that we honor the likelihood, we honor the data once we get that. So in that case, the credible interval is the probability theta is contained in that interval given the data is 0.95. Let's give just an overview of that. The statisticians are divided into two armed camps, the frequentist and the Bayesian, and there is a 250-year-old argument between these two camps. Sir Ronald Fisher, who is the founder of frequentist statistics, or what you call the classical statistics, and Reverend Thomas Bayes, who was the founder of Bayesian statistics long back in 1760, whereas the Sir Ronald Fisher's idea came up sometimes in 1870 or something like that. Okay? So there is a tussle going on and on and on between the Bayesians and the frequentists, but it's a good news that recently the people, both the frequentists and Bayesians, are coming to merge their opinions so that ultimately a reconciliation is expected to come in future. Once again, I said that the Bayesian approach respects the likelihood principle. So it's based on once the data X, say, at hand, it works throughout with the particular data set. On the other hand, in the classical procedure, you can change every time the confidence interval you can construct. It depends on the data set you have. So as the data varies, the confidence interval also varies, right? And one can see to that like the p-value, which is a probability the data or function of the data or more extreme under the null hypothesis H0. This is the p-value, and the p-value varies when the data varies, right? Optimal rules in the classical sense turns out to be the Bayes rule. Now let's start the Bayesian concept, more details. Bayesian use priors. What is a prior? Prior is non-experimental knowledge. A lady tasting tea poured into milk or vice versa. A drunken man predicts coin toss. Each of the 10 times they got it right. Now what happens here? You see that irrational people always think of that it is very difficult to say that whether when you toss a coin you get head or tail. It's very difficult to predict because the chance is 50-50 whether head will come or tail will come, right? Or it's very difficult to say whether tea poured into milk or milk poured into tea, right? But in both cases, the lady and the drunken man predicts rightly. So what is happening if you are in the classical procedure, you go for testing the success probability that the forecasting or the prediction is right, the success probability, if you call it theta, to be half. It's very rational to take it because it is random. As I said, that 50-50 chance that whether you get tail or you get head, right? Then based on the data set, if you just carry out your statistical inference procedure, you will see the hypothesis is automatically, it is very crystal clear here. If you look through that, it will be coming out the hypothesis is rejected. So what is rejected? They rejected that the randomness, that the theta or the success probability is not random is established from the testing procedure. But you know that rational human being always thinks that the theta should be here random, that is chance is 50-50. So unless you use some prior idea, unless you use some additional information, you are not able to properly draw your conclusion based on the data set you have. But on the other hand, in the Bayesian setup, if you vary your prior assumption on the distribution of theta or prior belief on the distribution of theta, inference may vary, but for given data set, you are going to draw your conclusion in the Bayesian setup. So what is Bayesian machinery? The Bayesian machinery is that you start with a prior belief on the state of nature or state of uncertainty, which is theta, and you use your data set, combine these two, and then you draw your posterior belief. And in the case of, we treat it in some other way. If you think of prior distribution for the parameter of interest theta, which is random, and if you use the likelihood, then you combine these two, you will draw your posterior distribution, and you can draw your conclusion based on the posterior distribution. So essentially, symbolically, you can see that the pi theta and L theta, which is the likelihood of theta given the data, are combined. These two are combined to get ultimately the posterior inference. So once again, if you look through that pi theta given x or the data is a multiplication of the prior distribution of theta multiplied by the likelihood divided over the marginal distribution of the data. So because the data is random there, so Bayes' theorem says that this is the marginal distribution. Now what we have, what is Px? It is over the distribution of theta. If you integrate the joint density of the prior and the data, or prior and the likelihood, you ultimately get the marginal density of data. So from this Bayes' theorem, you can say that pi theta given data is proportional to pi theta and the likelihood or Px given theta. Keeping that, I said that it is proportional. This is the reason is that the marginal density, which is a function of the data, can be kept to be constant here because we are interested in pi theta given data. All right. Essentially, the whole idea crops up from the Bayes' theorem, where the Bayes' rule is this: in terms of the conditional probability, probability C given D is probability C and D divided over probability D, or the other way around. If you just write in the other side, take it in the other side, you will get this. Probability C and D is probability D, probability C given D. So basically, from that viewpoint, Bayes developed the Bayes' theorem, that suppose D stands for the data and theta is the parameter of interest, then the posterior probability P theta given D is P D given theta, P theta divided over P D given theta, P theta, P D given theta complement, the complementary event, complementary sets of parameters multiplied by the probability theta bar. Very nice example is there to motivate the use of the Bayesian theorem here. Suppose an alarm is sensitive to both burglaries and earthquakes. In Sikkim, earthquakes happen fairly frequently. You are at a place far from Sikkim, but in phone contact with the alarm. You observe the alarm ring. A, alarm goes off. A complement, alarm doesn't. Incidentally, I just want to say that the term alarm goes off means alarm rings, which is very funny in the sense that it goes off. The idea is that when you say that a bomb goes off, that means a bomb blast, a bomb blows up. Okay. Similarly, when the alarm goes off, it means it was activated, but it just stops activating when the ring comes up. So alarm goes off means alarm rings. All right. Let's come back to that problem. The alarm could be due to a burglary or an earthquake. These are assumed not to be observed. Okay. And B, the symbol I am using for burglary, B can take the value 1 or 0 according as the burglary takes place or not. Similarly, E are indicating the earthquake. So E is 1 or 0, sort of dummy variable I am using, according as an earthquake occurs or not. Let's look at the likelihood here. The likelihood is concerned with what is observed. We observe whether the alarm goes off or not. So it's based on the data. What you have, probability the alarm goes off given a burglary as well as an earthquake occurs is 0.607. The chance that alarm goes off given no burglary but an earthquake occurs is 0.135. Similarly, the other two, when alarm goes off given a burglary occurs but no earthquake, no burglary, no earthquake occurs, still the alarm goes off. Okay, so these are the chances. So this chance, as you see that the no burglary, no earthquake occurs, but still the alarm goes off, chance is very little chance. Okay. The prior distribution I am talking about, the parameter theta, is the prior governs probability distributions over the presence or absence of burglaries or earthquakes. See, the prior idea comes from some previous study or somewhere that probability burglary occurs, very little chance, 1% chance, so 0.1, not 1%, it's 10%. And similarly, earthquake occurs, having the probability, the chance is 0.1. And we assume that there is no relation between burglary and earthquake, which is very straightforward assumptions and natural. The priors characterize available information about burglary and earthquakes. Focus is to find the probability. You see, what should be our focus? It should be that I am looking for the chance that a burglary occurs given the alarm went off, and also I am looking at the chance that an earthquake occurs given the alarm went off. Okay, so these two cases might be of interest to me. You see, the other way around, we got the likelihood, right? Alarm went off and the burglary occurs, or alarm went off and the earthquake occurs. We have the data, we have the information for that. So the likelihood is basically that one, the chance or probability that the alarm went off given that burglary did or didn't take place, and or oblique the earthquake did or didn't take place. The prior is the probability that the burglary didn't take place or earthquake didn't take place. Now we use the Bayes theorem for burglaries. What you do, we first of all update the likelihood relative to earthquakes and then use Bayes rule to calculate the probability of interest. Very simple to do that job. You know, you have the probability A given B equals to 1, E equals to 0. That means earthquake doesn't occur, but burglary occurs, and then we are looking for the alarm goes off. That means alarm rings. So chance of alarm ringing when burglary occurs, but earthquake doesn't occur. So we want the marginal probability, I should say the marginal conditional probability. So what is the chance of alarm ringing given that burglary occurs? That's fairly what we want to do. Now this is basically based on these two sums. One is probability A given B equal to 1, E equal to 0 into probability E equal to 0, chance of earthquake doesn't occur, plus probability alarm rings given burglary occurs and earthquake occurs multiplied by the chance of earthquake occurs. That we compute. This data set we have at our hand because we know the likelihood here. We know the likelihood here, the probability that I have shown you earlier, right? I have shown you these probabilities. So I am going to show this once more. I am going to compute this once more, and then what we have, that the chance that burglary occurs, the chance that alarm rings given that burglary occurs is 0.3919. Similarly, the chance that alarm rings given that burglary doesn't occur is computed in a very similar way to be 0.0144. So I use the Bayes theorem here, and then I find out the probability that burglary occurs given that alarm rings. So when alarm rings, then I will have some idea whether the burglary occurs at my home or not. Okay? So this basically what you want to get is, based on this Bayes theorem and all this computation, comes out to be 0.751. So what is my conclusion? My conclusion is that out of the 100 times the alarm rings, in 75 cases, it is due to burglary. So let us try to give a diagrammatic representation for that. And what we see here is that what we have done in words, it's essentially graphically it has been represented. So you have the probability B equals to 1 equals to 0.1, the chance of burglary occurs, and then you know that you have computed the likelihood 0.3919 is the chance that alarm rings given burglary occurs. So then these two, when these two are combined, we get the probability B equals to 1 and A. So it is the joint probability that alarm rings and burglary occurs. So that comes out to be 0.3919. Similarly, we can combine probability B equals to 1.1 and multiplied by this conditional probability to get ultimately the other one, that probability A complement given B equals to 1. So it is the joint probability of A complement and B equals to 1. That means burglary occurs but alarm doesn't ring. So we can also compute that probability. Similarly, we can compute the other two probabilities here and here. So that whole thing. So we have two boxes here rather. One is probability chance of alarm rings and burglary occurs is 0.3919, and chance of alarm rings burglary does not occur is this. And if you add these two, you get ultimately the chance of alarm ringing is 5% case. So roughly 5% or a bit more than that, you have the chance of alarm ringing. Okay? So here we have just shown that how to compute that 0.751 probability here. Last time, in the last slide I have shown, right? We can do the similar thing for the earthquakes. I just skip this thing because the idea is very similar to what we have done for the burglary case, and we have the similar scenario here for earthquake case, and compute the accordingly the chance of alarm ringing given earthquake occurs. So all these things can be computed in a very similar way. Okay. Now, one other thing you might note that in the previous diagram or also in this diagram, what we are doing here is that we are assuming the prior assumption about the earthquake occurring. So what is the chance of earthquake occurring? So basically this prior assumption is not a very idealistic, it's not very artificial assumption. It's based on the meteorological data you have seen earlier. What are the cases of earthquake occurring in a year in Sikkim? So this is how the chance of occurrence of earthquake has been computed there. Okay. So we are using these prior probabilities and we are combining this with the likelihood or the data set that you have to get ultimately the posterior probability. Students, I believe now you have got some idea about that, how a Bayesian inference differs from the classical inference. You know, that in the case of classical inference, what I said basically that the likelihood varies, but theta remains fixed, and we draw our inference on theta as for different values of the sets of values of data set. So inference, the variation on theta is basically a function of the data set. But in the case of Bayesian inference, the scenario is totally opposite. In that case, likelihood remains fixed, but the data varies, the parameter varies, and in that case, the inference is given the data, you draw your inference from the parameter theta. Now we have tried actually to motivate our Bayesian inference technique by using the burglary and earthquake problem, and what we intended to show here is that in many situations where the classical technique fails to draw conclusion, the Bayesian technique can be used to draw inference that way. So this burglary earthquake problem is otherwise very difficult to solve by using the, or it should be, on the other hand, it should be irrational to solve by using the classical frequentist or Fisherian technique.